All right, well, you might be wondering what the lab engineer for the Austin district is doing talking about concrete pavements, but Austin district is not just a hot mix district anymore. I did highlight for y'all in yellow all the CRC in the district, and I don't know if you remembered from Wa's presentation, but the Austin bar graph for the lane miles of CRC is actually measurable. You can actually see it. So we might be a happy hot mix district in a lot of areas, but we also have some very good performing concrete pavements. You saw a very similar graphic to this in Wa's presentation, and where this came from is if you are the lucky grad student working for Moon Wan, what you get to do is crawl on your hands and knees and look at CRC Destresses all over the state for days and days. And in this case, for this particular project, they looked at every single distress identified in PMIS in these 6 districts. And then they classified them into what kind of distresses they were. If they were spalling, you know, that deep spalling that we get from those high coefficient of thermal expansion aggregates, or whether they were a real punch out because of structural insufficiency of the pavement, or if they were failures at a repair joint or failures at a construction joint. But Moon kind of changed the terminology of his acronyms on me because the 47%, the big spalling, that BS, I thought that meant something else when I pulled in this graphic to my presentation. Because in terms of a structural failure, that is a BS structural failure, that big spalling, right? It's nothing structural, it's just purely functional, the top inch or so. And so what we're really talking about today with transverse construction joints is this 21%. So for these 6 districts, a fifth of all of their distresses occur at a construction joint, and the vast majority of them being a transverse construction joint. So if you've never seen a failure at a transverse construction joint, this is what I'm talking about. You get, you know, anywhere from 6 to 18 inches away from that joint, and you start getting little chip outs like this that become pretty big over time. So there's another example a little earlier in the process, right? You get a little block crack, then that pops out of there, and then it just keeps going from bad to worse. So typically what maintenance will do is they'll throw a little cold mix in there, smooth it up over and over and over again. And this became a topic of extreme interest for me when I was working at the construction division lab out in Cedar Park, because every single day on my way home, that was the failure of the transverse construction joint I would pass over. And it just would make me so mad every single day on the way home. It probably would have been more productive on the way to work, because then I would have been really motivated to solve it. As it was, it just made me really irritated by the time I fought through traffic and got home. But this is a view from Google Maps, right? That failure that you can see where, again, maintenance has gone out there with some coal mix and thrown it in that hole. And then you do street view, and you can see in this case it's not coal mix. They actually have some sort of cementitious repair material in there. But that's probably not going to last particularly long either. So if you think about what is going on at that transverse expansion joint, right? Why do we get those failures? And if I had a treat, I'd throw it out to the first person who could identify one similar thing that these all have in common. Come on, somebody, help me out. They are right next to a joint. And do you notice they're only on one side of the joint? Right? They're only on one side of the joint. The steel on the left side of this joint is exactly like the steel on the right side of the joint, but for some reason, fine, not fine. Fine, not fine. Fine, not fine. Right? So there's something that we really need to think about and analyze and exercise all of that training that we've all forgotten about when we were getting our degrees. But fortunately, we don't really have to think about it too hard because we have plenty of smart university types doing this kind of research for us. And in this particular research project that I've referenced down there, sorry, I don't have my glasses, 6687, which was really a training module put together for how to prevent premature deterioration in CRC. So it was kind of a synthesis of all the work that was done really since about 1995 to about 2013. And one of the things in this synthesis is measurements of shrinkage strain at the transverse construction joint. So what the researchers did was they put strain gauges and distance LVDTs at various parts of the construction joint and then measured that strain over time. Do I have a... Okay, I got it. All right, so you can see, the various strain measuring devices they have at those steel bars, at the transverse, the nighttime or daytime header. And then here are the strains. So in the outside, the center, and then I don't know why they call that inside. Anyway, so they've got 3 different LVDTs all at the same vertical distance, but at different horizontal distances. And essentially, the strains are more or less the same. But what's interesting is the magnitude of that strain is 0.2 of an inch in 2 days. So you think, wow, 0.2 of an inch. Well, that's not very much, right? Well, this is what happens when that concrete wants to shrink 0.2 of an inch and there's not enough steel running through that construction joint to restrain that shrinkage. So when I got called out to this project, it actually wasn't because of this. It was because there was a whole bunch of weird cracking way back here. Well, it turned out that the steel was only at about 30-inch spacings there. So not very much steel at all. And so what happens when this part of the slab wanted to shrink that 0.2 of an inch, man, those number 6 bars at 30-inch spacings, they were nothing. Right, so enough pent-up stress built up and just shattered those bars, which then sent this shock wave down the pavement and then had all this weird kind of radial cracking further down the slab. So one of the great miscarriages of my professional career is I've never been around when something like that happens. Right? Wouldn't that have been awesome to have been standing right there when all of those bars finally just ruptured all at once? I mean, man, that just would be so cool. Probably not so much for the contractor who had to go saw this out and remove it and replace it. That probably didn't make them very happy. But just from a concrete, just the magnitude of the force there, I mean, that's pretty impressive. Okay, so there is a lot of pent-up demand for that concrete to shrink. Okay. So let me give you another little tidbit of what could happen. Okay, let's go back to this. Let's say we left this in place. Let's say nobody caught it, and this joint with basically no load transfer capacity but also very little restraint at the ends. What would have happened if that stayed in place? Well, the shrinkage is already done, at least the huge shrinkage immediately, right? That's already happened. But you know what hasn't happened is expansion. Because now there's so little restraint at the end of this part of the pavement and at the end of this part of the pavement, right? Because there's no mass. There's no mass of the other part of the slab there to keep it from expanding. The steel, I don't know what happened to the bond quality when that steel fractured and sent little ripples, concussion waves down the pavement. But I'm anticipating that there's not particularly good bond anymore at the end between the steel and the concrete. So both of these slabs are fairly unrestrained there at the end. So if we look at what we know happens at the end of a concrete pavement, right, where we tie into a bridge or where the concrete pavement just ends, what we know from, see, where's WAS? See, at least I credit when I copy and paste stuff people have already presented to save me from having to do some work. At least I give them credit. But what this research showed us, that for a simple expansion joint, if you had 100 degree of temperature change, which that's not really all that unlikely, from if the time, if the placement temperature was fairly cool and then we have a hot day and that concrete gets hot, man, that's a little high, but it's probably not out of the range of reasonableness, that we could have a delta T of 100 degrees, that we get basically an inch of expansion at a simple expansion joint, right? So I look at that kind of like as an unintended simple expansion joint, right? So yes, that thing shrunk 0.2 of an inch plus, but at some point in time, it's now going to want to expand an inch. So if we don't restrain the ends here at this transverse construction joint, it's a two-directional movement that concrete pavement wants to experience. So what do? We all know, everybody took the reinforced concrete class, right? What do we do to prevent concrete from cracking up too much? Well, we restrain it with steel. So let me pose a question here. So this comes out of the current CRC standard. It's actually very similar to what's been in previous CRC standards. But let's take a 13-inch slab. So we have a spacing in between longitudinal bars of 5.5 inches. Okay, number 6 bar, that's 3/4 of an inch diameter. So the clear spacing now is 4 3/4 inches. Am my math good? All right. Okay, so if you go by the ACI rule of thumb, that you ought to have a clear spacing between bars of a 4:1, the spacing to nominal max aggregate size of 4:1, okay, that means we're looking that we better not have too much more than a 1-inch top size rock. So we're probably okay, right? Even at grade 2, we're probably within that 4:1 ratio. But the problem is, at that header, because we're so worried about all that movement, historically we have come to put 50% extra steel at the header. So the way I look at it, right, these are all longitudinal bars, long, 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 long. So we come in and every other pocket we put in an extra short bar to help restrain all that movement at the end. Okay, so now we're no longer at a 4:1 there, right? We're probably more like a 2:1. It's still okay, right? Those guys, they're good with the finishers. They're consolidating it great, right? So here's really, I think, where we've come into a lot of problems, where we've really shot ourselves in the foot just with basic fundamental, concrete design and placement. So here are the long bars. There's that extra bar I was talking about, right? No problem. Man, but take a look. Right now, we're even complicating it because now somebody is trying to splice the long bars onto the long bars coming through. So I guarantee you there is no way that concrete is getting consolidated around or under those bars. So sometimes there's such a thing as too much steel, right? This is too much steel. This is not restraining that joint. That is just giving us more constructability issues. So in the 2013 standard, there is this new note, no splicing within 10 feet of that joint. So for every area engineer, is there even an area engineer in here? Yay! All right, awesome. Thank you very much for your attendance. Please tell your inspectors, right? Hey, man, let's highlight this because this is really important. Because remember, 1/5 of all the distresses in your CRC are going to be right there. So anything they can do to make this better is going to really help the long run. All right, so what else can be done? Right, there's really two problems, right? There's the shrinkage potential of the concrete, and then there's the steel's ability to manage that volume change. Okay, so reducing shrinkage potential. Well, we can improve the concrete mix design, make it less shrinkage prone. I've seen some contractors actually bring in a different load of concrete, like they'll bring in a ready mix truck with the higher slump for this work right at the header, right? Because there's no way that paver is backing up and is starting right at the header. All of that's going to be done by hand. So why make the finishers, try to finish this 1-inch slump, rocky, really harsh kind of pavement. So I have seen contractors bring in a higher mix in there. So that's great from a workability standpoint, but that's probably a more shrinkage prone mix too, right? So where's the trade-off? It's probably better consolidated, but it has more water in it, so it's probably going to shrink more. So that's a tough call there. We could cure it better, but then we've always been saying that, oh, we need to cure our concrete better, right? Or we can actually do something to change the design of the steel at that joint. So there is some work. It's still fairly preliminary that's looking at some fundamental design basis to come up with a better transverse joint. I don't know much about it. I think it's still early, so stay tuned on that. But I'd also like to propose for consideration, not that I'm in the market to get funded for research, but if anybody has the ability to look at this, if we combined what we know from a couple of other different projects, notably what we know about bonded concrete overlays, right, a couple inches of concrete directly on top of an older CRC pavement, what we know is if we put welded wire fabric or number 4 bars at that interface, that helps that bond, right? Because it restrains that fresh concrete from shrinking too much. Well, isn't that exactly one of our problems at this header, right? So maybe we could do something, not just at the neutral axis with the steel that's already there, but maybe we can do something to help improve the bond between the fresh concrete and what's that black stuff at the bottom called? What do pavement people call that? A bond breaker, which we really want it to bond. It's not a bond breaker at all. So maybe if we put some welded wire fabric, we can actually improve the bond to the bond breaker, and so provide some additional restraint, reduce some of that shrinkage. Maybe I don't know. But because I always do things backwards, now I want to put this all into perspective. Because you see pictures like this, and you go, man, that's some bad stuff. And I know I'm the equal opportunity speaker in the hot mix session, so I know all the hot mix people are like, going, man, that looks really bad. So just to put it in perspective, okay, this is what we're talking about. If you look at the performance of CRC, overall in the network, it's pretty good, right? 90% 90% of CRC has a distress score of 70 or better. And if you look, man, it's held steady. I mean, I could have pulled up older PMIS reports and it would have looked just like this, you know, going back 2007, 8, it would have stayed at about 90. So from a pavement type, CRC is doing really well. And then you add on to the fact that all of these that are at 90, or that are at 90% that are at 70 above, man, look at the age of some of these pavements, right? Yeah, we've got some new pavements in there. This is total number of distresses per lane mile here. This is the age. So, yeah, we've got some distresses in our 10-year, in our younger than 10-year. If we go to 15 or more, oh man, it's looking like a lot of distresses, right? So let's just take let's take the 20-year, more or less. One distress per lane mile. So we've got a 20-year-old pavement with one distress per lane mile. So that's really very excellent, right? And here's what's even more excellent, is that of these distresses, the one per lane mile, 47% of them, those are those BS punch outs, remember? Okay, we're not going to have those in the future. Of course, the pavements that are already down are going to have them. New pavements won't have them. Why? Because we've had this coefficient of thermal expansion requirement of the coarse aggregate in for several years now. Okay, I did these out of order. Okay, if we could eliminate these transverse construction joint, this 1/5, that would be great. Because between the two of those, that's what causes these repair joints, right? So if we can fix the 47%, which we did, if we can fix the 21%, we get rid of that 18% anyway. So all we're left with is the 14% real punch outs, which we know how to eliminate. Tied shoulders, good non-erodible bases, and then we'll be down to 0 distresses per lane mile for any new pavement built in the future. And if you believe 0, I've got something to sell you. But the point is, it's low, right? It's going to be real. 1 per mile is low. Less than 1 per mile is even less. See, that's Aggie math. All right. And one of the things too that I want to point out is that all of this, the changes to the standards, all of this knowledge came from TxDOT's really strong relationship with universities, right? So this was done largely before the research apocalypse or research-ageddon, right, which is over now. And so we have the opportunity now to make some progress and solve this transverse construction joint. And I really think before my career is over at TxDOT that we're only going to be seeing those on old pavements. We're not going to be seeing them on new pavements anymore. How am I doing on time? Excellent. So I've got 5 minutes, so y'all can either ask me questions or I can tell jokes. And so it's probably less painful if y'all just make up questions just to keep me quiet. Okay, a guy and a dog walking. Oh, yes, sir.
One of the things that I've noticed where I've seen some problems has been that in construction joints, the contractor can basically do 100% splicing, effectively tie-in the whole thing. Something else there to help improve that.
Man, I should have brought my glasses up here. Okay, because I had some backup slides too, Amy. So the question is, sometimes when you're tying into an existing pavement, what do, right? You can't extend that steel, right? You know, you can't go back in time and run that steel through the joint. So you're really almost forced to have those splices somewhat close to that header. And so let me posit two things to you. And you know, this is the first presentation I've really given since I've needed reading classes, and it's really hard to try to find stuff. Okay. I can't even find that little. Ah, there's the trick. See, look in the big thing. Okay. So let's say hypothetically, you know, we were on this was the end of our old pavement, and we were trying to tie into this side. Well, this pavement, it's already done, it's already had most of its shrinkage that it's going to have, right? Let's say it's 15, 20 years old. So it's already shrunk most that it's going to shrink. And it has great tensile strength, unlike brand new pavement 3 days old, you know, 2 days old. So if I have all these splices on this side, I'm not really worried about the shrinkage of this new pavement pulling that pavement, right? Because the old pavement has the tensile strength to be able to handle that. And so what the standard, the CRC standard has is it gives you two options. It gives you a drill and epoxy because it knows, okay, this has the strength, so you can drill and epoxy those bars in there, but instead of a bunch of short little bars, it's going to make you stagger those drilled and epoxy bars. So at an intersection, that might not work. But if all you're doing is tying into an old pavement and, you know, going down the road, that would probably work, and then you really wouldn't necessarily have to worry so much about this happening on your new section. There is an option in there. It was put in after April 2013, meaning I don't like it, which is a breakback option, which is you literally jackhammer out, like, what is it, 30 inches, where's Waller, Andy, 30 inches, 36 inches, you jackhammer it out and expose the steel, and then you tie the new steel to that exposed steel. And if you can do that without crapping out your old slab, I'd like to see more of that. Did that answer your question? Or no? Or are you talking about new to new?
Well, we've seen both actually.
Yeah, you know, at intersections, it's just hard, right? It's tight, you don't have a lot of time.
We've encountered is drill back into the old pavement, it seems all the impact goes, it's actually creating horizontal fracture lines.
Right, and I think, so his observation is sometimes when they have drilled into an existing pavement to establish new tie bars to the newer pavement, what they find is the impact just from the drilling operation will cause some horizontal cracking at the mat level. And so we have done a ton of looking at that over the last decade, and that horizontal crack was probably already there. What the drilling operations did was just kind of open it up, make it visible. So that is a real dilemma. If we're trying to tie into an already distressed pavement, right? What do? So there have been some projects where they go, okay, we'll just cut it back farther. Okay, well that wasn't far enough. Cut it back farther. Okay, well that wasn't far enough. And, you know, and they finally get to a point where maybe they're in some sound, non-cracked concrete. But more work needs to be done on that too, I think.
I think we'll take one more question. I see nothing.
Yeah, but we also have to give these guys a break and like not make this so constricted that they can't, they can't really vibrate it. But you're right. I mean, the two most tired people at the end of the day are probably the two people most likely to ensure the success or the lack of success at this transverse construction joint.